So, I just went ahead and it did the entire lecture right up. This is recording just to pad the front of it. But yeah, so here I'm going to be covering basically the derivation of PCA and also kernel PCA. And in this case, I'm following Bishop's book, and this is Pattern Recognition and Machine Learning. Bishop is sort of the definitive book for machine learning, and it's free online. You can go to Bishop's website and download it. It's you don't have to buy the copy that I bought, but it is fairly robust and rather satisfying to hold. So yeah, there you go. But yeah, so a few things I should mention before we jump into this. There are a few notational differences that we see between Bishop and Steve Brunton's book. I tried in the lecture to stick as much to Brunton's notation as possible, where he adopts the convention that all your vectors should be arranged as row vectors. But Bishop takes the other perspective where all your data vectors should be column vectors, which I do personally like better, but now I've already recorded that other one and said I was going to do the other. So I apologize for that, but yeah. Anyway, so I try to stay agnostic as much as I could, but eventually you just really have to talk about the actual arrangement of these to really show that you're getting a matrix out of it. And I guess, so following, so the lecture here is going to follow Bishop's convention, and what's nice about Bishop's convention is that it also feeds really nicely into kernel PCA. And so also where Steve Brunton gave the definition between as for the covariance as coming from the multiplication of the transpose of a matrix times the matrix itself, Bishop starts out by writing the variance and then extracts the matrix out of that. And if we follow that convention, we basically get the rank 1 summation formula that describes our covariance matrix. From here, it's a natural extension to talk about kernel PCA, and so I decided to really follow this one a lot closer, and so you'll see how that all plays it into here. Kernel PCA is inherently infinite dimensional, and so what we're going to end up doing is we're going to find some ways of avoiding dealing with infinite dimensions, and this is generally called the kernel trick. And so we're going to do some extra multiplications to reduce everything down to matrix as n by n. Also, I should note that in Steve Brunton's book, he divides by 1 over n minus 1, where n is your number of data points, whereas Bishop divides by just 1 over n for the covariance matrix. Now, as far as the actual principal components you get out of the matrix, they're not really going to differ by much, just like a very smidge of a coefficient, and so it doesn't really matter when it comes to actually representing your data, but just if you find it confusing between one of my lectures and this one, that might be the source there. In any case, so I think I'm done recording for the morning, and yeah, so I'll put this up this week, and then I should have some MATLAB lectures coming together. I'm going to put another intro video that'll also lead here, honestly, for kernel PCA, just because I think it would be nice to have a quick 15-minute discussion, and probably if you're in the future, this might be how you got here. And I guess, but I need to give my students a lecture, and so here we are. Anyway, so let's go ahead and jump into it, and you'll see exactly what I'm talking about. Okay, so let's go ahead and get started and take a look at the PCA. Oh, that's a big marker. That's too small. That's good. That's good. All right, so we're going to talk about the PCA. And so in here, we have a collection of data points. And these are indexed by 1, x1, x2, x3, etc. Up to some fixed n, which will just be, say, capital N. And this collection of points is in RD. For some finite d. And so the goal here is to project, we want to project these data points onto a lower dimensional subspace. Of dimension m. M, which should be less than d. Preferably it is way less than d, but we'll see. And so we're going to assume that m is given. And here I'm following Bishop, by the way. And so this is Bishop's text on pattern recognition and machine learning. Right, and Bishop's text, again, you can find free online. So if you want to go and get that, then yeah, feel free to. So, and so basically the way we're going to do this is we're going to try to come up with an orthogonal set of vectors. So we want an orthogonal set of vectors, collection of vectors that maximize variance. Okay, and so the first thing we need to do is we need to figure out the average of our data set. So I'm going to define x bar, and that should be equal to 1 over n times the sum, say, over I going from 1 up to capital N of xi, right? And if I take another vector and I take the dot product here, so I take u dot x bar, I'm avoiding using a transpose notation because Bishop actually uses column vectors, and whereas Steve Brunton in his book, he uses row vectors for his data, and so trying to steer away from being decisive about which one I'm using. Just know these x's are in Rn, and if you're doing this sort of inner product, then basically you need to have a row vector times a column vector. However you need to do that, if you need to transpose something or whatever, just make sure you do everything in the right order. All right, so basically this is u dot with the sum I equals 1 to n, 1 over n here, of xi. And so that means that u dotted with x, and the average of this is going to be the same as u dot x bar. So that means if we want to compute the variance, then then it's basically going to be, you take the average, sum 1 over n of n going from 1 to capital N of u dot x minus the average of u dot x squared, and that's going to be the variance here. Now this can be written out as, say, u times s times u again, and well, now I have to say, okay, so I guess I'm having to decide here that we're doing column vectors. Okay, well, I was trying to stay agnostic, but yeah, there we go. I could keep doing some gymnastics to get around this, but it's just going to get confusing. So then we can, so we can express this as a matrix here like this, whereas u is on the outside and s depends just on our data points. And so then what we end up doing is we're looking at, say, 1 over n, the sum, n equals 1 to n of, we take the dot, we change a square for dot product with itself, and then you can go ahead and extract things. So we can, say, factor out u out of here. So it could be u dotted with x minus x bar, and this quantity squared, and that can be written as sum of 1 over n, sum n equals 1 up to capital N, and we have u dotted with, well, let's just go ahead and be explicit, x transposed with x minus x bar, and then we have x minus x bar transposed with u. And then we can factor out u's because this is a linear transformation. And so what you end up getting is this. This is the same as 1 over n times, or rather, say u transpose times 1 over n times the sum n going from, or I here, sorry. Should have had an I. Should have an I. Sorry, I don't know why I fuzzed out there. But okay, so then you get this, x minus x bar times x minus x bar transpose times u. And again, so I'm taking these x's as column vectors, which is in opposition with what we see out of Steve Brunton's book. But hopefully it doesn't confuse too many of you. But yeah, so this S is exactly this matrix that you get here. So with the perspective that this is going to be column vectors, you're basically making a whole bunch of rank 1 operators here, or rank 1 tensors, and you're constructing S out of it. And so we've exchanged our problem here as a problem about statistics and variance, and we've turned it into a problem straight out of linear algebra. We're now our goal is to maximize the variance that we get out of here. And so now we maximize the variance, the projected variance. And that we know now is represented as u transpose S times u. But we would like to be able to get add another constraint here where u transpose u is equal to 1, or rather the norm of our vector is equal to 1. And so now with this extra constraint, let's say, so with this extra constraint we can make a Lagrangian. And so and this is for so we'll say LU if you want, plus some lambda times 1 minus u transpose u. All right, so this is an optimization theory trick to sneak in some equality constraints in an optimization problem. So if we look at this as a variable of both lambda and u, then if this has a stationary point, then that means that the derivative when you take the derivative with respect to lambda, you set equals 0, that actually ends up giving you u transpose u is equal to 1. And so then this in combination will allow us to do a sort of an unconstrained optimization, where here we had a constrained optimization problem. And so if I go ahead and take a look at the partial derivative with respect to u, and so I can just say take the gradient with respect to the gradient with respect to u of L, say lambda u, then what do I end up getting is I get 2s times u plus lambda times negative 2u, right? And then if we want to set this equal to 0 to solve the optimization problem, then what we end up getting is this. We have SU is equal to lambda times u. And hence, lambda u is an eigenvector for S. And so then and with eigenvalue lambda. Okay, so at this point, what we know is that we select the eigenvector, say u1, corresponding to the largest eigenvalue of S, right? And that eigenvalue we'll call lambda 1. And this is going to give us the largest value that we have, because if we know that u has to, since we're looking to maximize this quantity, say u transpose SU, well, we just showed that u has to be an eigenvector if we're going to do that. And so then we're going to end up having u transpose times lambda u, and this is going to be lambda, and we said that u transpose u is equal to 1, so it has to be equal to whatever the eigenvalue is. So this is the variance, the projected variance. And so if you want to choose the biggest one possible, well, you choose the largest eigenvalue, and that gets you that. Okay, so that's more or less how you do this. And so then you just continue by adding constraints that say we're looking for a u2 that is, say, orthogonal to u1, but also u2 transpose u2 is equal to 1, and etc. And then you can continue going down this path, and then that will give you all the other principal components of the system. And so this can be done by induction, or if you rather, you can just go ahead and use the fact that S is a symmetric matrix and expand out its eigenvector equation, and you can arrive at all these same quantities in just the same way. And there's a if you look up a proof for for PCA on Stack Exchange, there are people there who do that too. Okay. So now that we've seen regular PCA, let's talk about the formulation that comes with kernel PCA. And so here we have something that we call a feature map. And so this is a map psi, which goes from, say, RD to little l2 of n. Little l2 of n, if you don't know, is the sequences, say x1, x2, etc. It goes off to infinity, such that if we take the infinite series, I going from 1 up to infinity, of xi, and we look at those magnitude squares, this is finite. So this is what we're going to end up calling a Hilbert space later, and in some sense this is every Hilbert space. Once you expand them into their orthonormal basis, you can always map them back to little l2. So, this idea is fairly far-reaching. Now we're not always going to be mapping to an infinite feature space, and so sometimes you could think of this, even though it's mapping from RD to little l2 of n, that maybe after a certain point all you're going to have are zeros, and so and that would be the case, say, for the polynomial kernel and things like that. So, one example of a feature, super simple. If x is just in R1, would be the mapping to 1, x, x squared, x cubed, etc. And this would actually end up giving you the Hardy space kernel. And in a sense, you can see that it basically breaks down the point x in terms of polynomials. And so linear polynomials, quadratic polynomials, cubic polynomials, etc. And you can, and in a similar sense, you can get the exponential dot product kernel if you just divide by, say, 1 factorial square root, 2 factorial square root, 3 factorial square root, etc. And that'll give you the exponential dot product kernel, which you can use to do, say, function approximation. And so in that case, you take a function, and ultimately what you're doing is you're breaking it down into, say, each of these features, which are basically monomial features. So ultimately, what we're going to do is we are concerned with the kernel function that corresponds to this. And so, say kxy is a kernel function, and if we think of these guys as being, say, column vectors, so say transpose, then what you have is psi x transpose psi of y bar, right? And this is going to be a sum, say I going from 1 to infinity, of psi I at x, psi I of y, where psi I x is the component from the infinite from this infinite sequence of psi. So we're thinking of, the map of x goes to psi 1 x, psi 2 x, and etc. Okay, so now what we're going to do is we're going to end up posing all of this framework of a PCA in terms of the features. So the idea is that we're mapping something from we're mapping this x into sort of this infinite space, and so it's another space that is sort of higher dimensional. I don't know how to represent higher dimensional, but basically we're mapping it to another space, psi x, and we're hoping that the problem is going to become linear in this space where it might have been nonlinear over here. And so but once we do that mapping, we can go ahead and try to do it. So we have data points, and this is going to be, say, x1, x2, all the way up to, say, x capital N inside of, say, RD. And then we're going to compute the covariance matrix again, and just remember, like last time, we ended up having this. So the sum of I going from, let's say, n going from 1 to capital N of psi of xn against psi of xn transpose, right? So remember, this is going to be a column vector times a row vector when we transpose it, and so this ends up giving us a rank 1 matrix that is infinite dimensional. So it's an infinite dimensional rank 1 matrix. Now, I mean, here I'm also assuming, though, we're making the assumption that the sum over n of psi of xn is equal to 0, right? And so we're assuming that there is sort of a zero mean or centered data points in the feature space. And so later we can come back in this. And again, I am following Bishop, and this is section 12.3. So just as before, what we're looking for is we want to maximize this variance. So we want to maximize, say V transpose C V, and in order to do that, what basically our intuition says there should be an eigenvector equation, and so then we're looking for C times V, which should be equal to lambda times V. Now, in order to get here, we have this problem where now we are trying to figure out exactly how to express this V in terms of this feature space. And so what we get then is we have sum of 1 over n times psi of x n times psi of xn transpose n equals 1 to capital N. Make sure I did everything. Yep. And now we're going to apply this to, say, V, and then we should get lambda V out of it. But if we put our parentheses around cleverly, we see that this is a scalar, and these are our vectors. And so then we get V is a linear combination of the feature maps applied to the data. Right. Okay, so that's what we get. So then we can go ahead and say V then is not just any vector, but it goes from n equals 1 to infinity, or n equals 1 to capital N of AI or AN times psi at xn. And so then we can go ahead and feed that back in. And this is what we end up getting. So we have that C times V should be equal to lambda V, but now we have that C times the sum of AN times psi at xn should be equal to lambda times the sum of AN times psi at xn. And ultimately this is this 1 over capital N sum n equals 1 to capital N of AN psi of xn. Sorry, forgot the actual matrix. And here we'll put little m here, just so, because we're going to have multiple sums within sums. But here C is this, psi of xn against psi of xn transpose. And now this is equal to lambda times the sum of an psi of xn. N equals 1 to capital N. And this is n equals 1 to capital M. N, and this one is m, remember. Okay, so now we need to solve this. So one thing that we can do that we can notice is that this guy against this guy is a scalar, and in fact it corresponds to our kernel function. So it's a sum of 1 over n times the sum n equals 1 to capital N psi of xn, and now we can move the actual sum inside. So we have the sum of n equals 1 to m equals 1 to capital N of a m times psi of xn transpose times psi of xm, right? And this is equal to lambda times the sum n equals 1 to capital N of an psi of xn, right? Now, I really wish I was one of the authors who came up with this trick, because I mean, like, this is what ends up happening after this is so slick that, I mean, it's really rather inspired. Okay, so in this case, I'm going to be thinking of the kernel function as a real valued kernel function. And so for now, we'll just delete this. In the future, we will want to have the complex version of that, especially when we talk about operator theory. But in a lot of data science, you don't really talk about that much. So we'll keep everything real. And if we do that, then we end up getting this. So this ends up being here. This is our kernel function, kxn xm. But we still have a couple of these guys hanging around, and we would like to get rid of those. And so we're going to take another one of our quantities, and let me go ahead and copy this to the next page. The wonders of the modern world. So go to the next page. Let's paste it, and you can get rid of the junk. All right. So what we're going to do now is we're going to do something rather clever. We're going to take both sides, and we're going to pick another data point, and we're going to multiply it by psi of xl. We're going to multiply here by psi of xl. And when I do that, you end up getting this. And I should say times transposed. So what ends up happening then is the whole equation boils down to this. It becomes 1 over capital N sum n equals 1 to capital N of psi of xl transpose times psi of xn times the sum m equals 1 to n of an times the kernel function at k xn comma xm. And this is equal to lambda times the sum n equals 1 to infinity, or n to capital N, of an times psi of xl transpose times psi of xn. And so this guy is our kernel function, kxl and comma xn, and this is a kernel function over here, kxl xn. And it turns out that all of this can be expressed in terms of what is called the gram matrix. And the gram matrix k, and so well, he writes k, but I can't really. Well, let's just bold k. So our matrix k, bold k, is equal to k x n x m, where n and m go from 1 up to capital N. And so this is a matrix, and it's a gram matrix, and it's invertible, and it's positive definite. And so then what we ultimately end up getting is this. We get k squared times a, which is a vector of a column vector of our coefficients for v, is equal to lambda times n times a times k times a. These are scalar, and this is a matrix. And so I guess keep my notation of scribbling like crazy. Yes, there's blackboard bold, but that's not nearly as fun. Okay, so I said k is positive definite, which means it's invertible. So I can go ahead and cancel it from both sides, and what I end up with is k times a is equal to lambda n times a. And so now we have a new eigenvector equation that we want to maximize. N is fixed, and basically we want to choose it so that lambda is as big as possible. And so we select a to be the eigenvector for k with largest eigenvalue. And there we go. And then you basically go on and you can do that, and you get a complete eigenbasis. So you get, say, a complete eigenbasis. So you have a v1, which is the sum of, say, a1n times psi of x n, n going from 1 up to capital N, such that we choose it so that v is 1 and n corresponds to lambda 1 largest. So this v is the largest eigenvalue for bold k. Okay, and etc. So that gives you a whole collection of eigenvectors. Now we weren't actually writing down everything in terms of centered data, and so we need to correct for this real quick. And so what we can do then is we can take a look at psi tilde of xn, and we'll write this as psi of xn minus the average 1 over n sum n equals 1 to capital N of psi of xn, right? And when you do that, you can make a new matrix equation, and so we're looking for, say, k tilde, and if we want each of the indices for k tilde, it just comes out as sort of this sort of combination here. So we get k and m is going to be here, right, as psi tilde of x n transpose with psi tilde at xm, and then just expand everything, and you end up getting this. You end up getting a kernel function at xn xm minus the average 1 over n going from I equals 1 up to capital N of k x I xm, and then by symmetry you end up getting this. You get sum 1 over n of sum I equals 1 to n k x n x I, and then you get plus 1 over n squared times the sum of I going from 1 to n, sum of j going from 1 to n of k xj xi. And all of this can be rewritten so that you can write this as k, bold k minus the matrix of ones of size n times bold K minus K bold K times the matrix of ones plus the matrix of ones times K times the matrix of ones, and then that'll give you that matrix. And so then that's how you end up recentering your data, and that's how it changes things there. Okay, and so at this point, I think I'll go ahead and close up, and in a couple days, I'll see if I can put together a MATLAB lecture to go ahead and accompany this, and so that we can actually see all this in practice, and we can talk about exactly how we extract information out of our projected kernels and all these other good things. Okay, so yeah, thank you for hanging there with me, and yeah, I'll go ahead and close up shop. Okay, so that was a construction of PCA and Kernel PCA. What's interesting is that in the construction of PCA, you could write this all in terms of maximizing the sort of eigenvalue equation, and then we'll actually see that come back into play when we start talking about spectral theorem applied to compact operators that are infinite dimensional. And so there we'll use this notion, and it'll allow us to get things like an eigen decomposition for compact operators, which will then allow us to talk about convergence of a lot of these data-driven routines that we're going to do for dynamical systems. In any case, battery on my camera is dying, and I probably should get going. But thank you for staying through this with me, and now hopefully we know a little bit more about PCA. All right, take care.